last thing, guys. And again, between my notes, the reading in this, and then Zoom conference, we should have covered just about everything. Nothing's perfect, but we're doing everything we can. So I wanted to go over the big equation here. So this is delta G, Gibbs free energy, delta H minus T delta S. So decipher what all this means. Delta G, this is energy available to do work. In your reading in my notes, this is thermodynamically favorable or not. If it's negative, it happens. That means you saw it do something. It's available to do work. If it's positive, it doesn't. That doesn't mean never. Just means it doesn't happen under these conditions. Now, there are certain things you'll see in your notes that it could mean never. You might be able to power it by pairing it with another reaction that's got so much extra energy you can make it happen. But that means the energy that's available to do work. So when I do your learning exercise, and I post the video of me doing a mini lab, if you see a reaction happen, it is thermodynamically favorable. It did something. So delta H we've done. And by the way, this is usually, the unit is kilojoules. This is enthalpy. This is your heat term. This is also in kilojoules. If it's negative, it's exothermic. So it gave off heat. If it's positive, it's endothermic, and it took in heat. Well, now we've got the last part that we've been doing. Delta S is entropy. Positive means dispersion. Or disorder. Negative means order. Here's the thing. This S term is in joules. So that means this one counts more. So the heat term matters more. So when you're doing your calculations, you need to make sure that if you're given like a delta S of like 150 joules, before you solve the problem, you need to change that to 0.150 kilojoules. Doesn't count as much. Okay? Keep that in mind when we're doing it. So, let me find my eraser here. You've got what all that means. None of the problems that I'm going to go through here in a second are going to use that equation, but you're going to need it for when we do our lab exercise. Okay? So I'm going to do from your NIMSY note packet problems 2, 4, and 6 to give you a little assistance. Okay? She's getting tired of me doing this. She wants some attention. We got to finish. Okay, so numbers 2 and 4. And again, I will post all of the answers online for you eventually, but I wanted to give you a way to look through these. So number 2 that was in your packet, and I'm actually going to read for you here, which I know is just terribly exciting. So it gave you a chemical reaction, sulfur dioxide reacting with oxygen gas, giving you sulfur trioxide. Great. Calculate the delta S for the process. Oh, I was showing you this one specifically because it was showing you that delta S is a state function doing products minus reactants. And if there's going to be a purist who watches this online, like, follow the numbers and follow the signs. Okay, so you've got values for entropies for each one of those. Note that even though you've got elemental oxygen, it's not a heat of formation, it's an entropy of formation in a manner of speaking. That's allowed, so you're going to have to factor that in here. So it's products minus reactants. Product, I only have one, but you have to put in your stoichiometry, so 2 times 256.3 minus the sum of all of my reactants. So 2 times sulfur dioxide plus my 1 oxygen. So I put that in parentheses, so 2 times 248.1 plus 205.3. Sorry, it got a little smooshed. I'm not perfect. So 512.6 minus, I still have it in parentheses, 496.2 plus 205.3. 512 minus 701.5 gives me a delta S, an entropy of a negative 188.9 joules per mole degree Kelvin. What does that mean? It's a negative delta S. That means disorder, dispersion decreased, order increased. Look at your reaction. 3 moles of gas going to 2. Fewer bonds, more bonds. A more ordered product. My answer makes sense. Okay? And the joy of working at home. My bird hates the phone. Jalapeno, you tell them. She really loves riding around in my hood, and she's also pooped on my back. Okay, number 4. So this is water reacting with oxygen gas to make hydrogen peroxide. And you have delta G values, or Gibbs free energy values, for the formation of each one of those individual reactants. So it wasn't asking for the delta G equals delta H minus T delta S. It was asking you to find the delta G for that reaction based off of each one of those values. So it's another products minus reactants. Oh, oxygen's elemental, it was a 0. This also did it in kilocalories, which you're not going to be asked to do much, so I'm not worried about it. I'm more worried about the sign here and you being able to do the math. So here's my delta G formation of the peroxide. Remember my stoichiometry, I'm going to have to multiply by 2, and I didn't put that in there. Joe Hussein, where are you when I need you? Dr. K, you made a mistake. Me. And then your reactants, negative 56.7 times 2. So a negative 54.4 minus a negative 113.4. So that's like doing addition. My delta G has a positive 59.0 kilocalories. What does that mean? Well, if you go back to what I just had up on my previous dry erase board, a positive delta G means not thermodynamically favorable under the conditions described in the problem. It's at 25 degrees Celsius, and we don't know what pressure. Oh, wait a second, I'm looking at the wrong one. Under the conditions described, it didn't happen. Now, can you make hydrogen peroxide? Sure, they sell it to us in a bottle. Did it happen under those conditions being described? No, it has a positive value. It is not thermodynamically favorable. Doesn't mean that it never happens, doesn't mean that it won't happen. It just means that under the conditions that were described in the problem, that it's not going to happen, okay? Doesn't mean never, doesn't mean impossible, just means that it won't happen here. I'm showing